For our project, we threaded a string through a PVC pipe and tied a 0.5 kilogram mass to the bottom end of the string and a 0.1 kilogram mass to the top end of the string. In an ideal scenario, M1 is going to swing around the top of the PVC pipe at a 90-degree angle. And we know from the centripetal force equation that the string is pulling on M1 radially in with a tension force of M1 v squared over R. And for M1 to remain in a uniform circular motion, we know it also must be pulling on the string with a reaction force equal to M1 v squared over R. And if M1 is pulling on the string with that force, the string must be pulling up on M2 with a tension force of M1 v squared over R. Now we know the force of gravity down on M2 is equal to M2g. So for the net force on M2 to be 0 and for M2 to remain stationary, we know that M1 v squared over R must be equal to M2g. But now let's see what happens when we actually test it. Something doesn't seem right.
Now, as we saw in the video, M1 does not travel at the same height as the PVC pipe. In fact, the string makes some angle theta with the horizontal. Now we know that there is some tension T in the rope. In fact, T, as we previously found, is given by M2g. Now we know the horizontal component of the tension is equal to M1 v squared over R. So we can set T equal to M2g and set that equal to M1 v squared over R. We know M1, M2, and G, and from the video we can analyze and find theta, V, and R.
In order to accurately measure and determine theta, V, and R, we mark the string in 5 cm increments as well as the PVC pipe in 1 cm increments. Let's go back to the video one more time. We filmed from 2 angles, one from the side and one from the top. The side view helped us measure the radius and theta, while the top view allowed us to determine the period of the swing. Let's stop at a still frame from the side view and do some calculations.
From the markings, we determined the hypotenuse and the height, which allowed us to calculate the radius using the Pythagorean theorem. Using the radius, we found the circumference. We counted the number of frames it took the swinging mass to make a full revolution and divided that by the frames per second of the camera to find the time of its period. And if we divide the circumference by the time of its period, we can find the mass's velocity. We also know that theta is equal to the sine inverse of the height divided by the hypotenuse. As we previously showed, M2g cosine theta is equal to M1 v squared over R. When we plug all the numbers in, we find that both sides of the equation nearly equal each other. You can see that it's not exact, but it does show that the principles of circular motion hold true.
If you still think circular motion is boring, consider this. If a spaced issue were to rotate about a center axis, all objects will be pushed against the outward wall. This would create an artificial gravity environment.
That's such a huge angle.
Yeah, it's a really big angle.
Oh.
Whoa!